Hey guys, this is the notes for lesson 5.1, but before we get to that, we need to review what we did. Shoot, was that back in chapter 2? I don't remember, when we did z-scores. So this would be the warm-up that we went through in class, but just to make sure we're remembering how we do it. First of all, this question is asking about 68% of your data. And if you remember, 68% of your data will be within one standard deviation of the mean. So the 68% will be less than a mean plus the standard deviation and more than a mean minus your standard deviation. So for this particular problem, that means that it's going to be less than 1500 plus your 200 and more than 1500 minus your 200. I could sketch out the standard curve that goes with it too, or you could just kind of visualize that it would be between 1300 and 1700. Now, if I wanted to find a z-score for a particular x value, as a reminder, the formula that you're going to have to keep using again this chapter is x minus the mean divided by your standard deviation. So for this problem, it turns into 1800 minus your 1500 divided by 200, or 1.5. So we're going to be using that today whenever we talk about normal distributions and the standard normal distribution. These are two different curves that are going to come up a lot, and they're represented a lot in statistics things, and we're just going to get an introduction to it. So first of all, the guidelines for your normal distribution. A normal distribution is a continuous probability distribution for the random variable x. It's continuous, meaning we're not going to make histograms. It's not going to have these bars. It's going to be one smooth continuous curve. This is called the normal curve. It's a normal distribution. That's just the name of it. It's going to be symmetric, so your mean, median, and mode are all equal. They're all in the middle. It is bell-shaped and symmetric about the mean, so half will be on the left of the center, half will be on the right. The total area under the curve is equal to 1, meaning 100% of the time it's going to be represented under there. Think of it like we do in probabilities. The normal curve approaches but never touches the x-axis as it extends further and further from the mean. So it's going to look like it's getting infinitely close to it, but it technically will never actually touch the x-axis. You'll see that in a second when we look at it. Between one standard deviation above and below, so the center of the curve, the graph curves downward, meaning it looks like it's cupped downward. But it cups upward to the left of that one standard deviation and to the right of the positive standard deviation. These are called points of inflection. So where it changes from looking like an upward cup to a downward cup, that's going to be at the one standard deviation away. And again, those are inflection points. We'll see that in an example in a moment. So just a bit of review, which normal curve has the greatest mean? Well, you're looking at the center of the curve where the mean is, then B would have the greatest mean because it's further to the right on your x-axis. But which one has a greater standard deviation? Well, we're talking about distance from the mean. So the fact this one's more spread out than this one tells me that B also has a greater standard deviation. The height of these are irrelevant. You're not going to use that for anything. For this one, the diameter of a fully grown white oak tree, they're normally distributed. The normal curve shown below represents this distribution. What is the mean of the white oak tree? Well, the mean is in the center of your curve, so the mean will be about 3.5. And I want the standard deviation of this normal distribution. Now, we're going to have to estimate this. We said the point of inflections happen one standard deviation away. So if you kind of look how the center of the curve look like it's cupping downward. But the outsides, like the right-hand side and the left-hand side here, look like they're kind of cupping upward. That, where it changes from one way to the other, is called a point of inflection. So around here, it kind of looks like going from cupping upward to cupping downward to cupping upward. So since that's happening at around 3.1 and around 3.9, I'm going to assume or estimate that those are about one standard deviation away. So I'm going to find the distance from that x value to the mean. So since that is about 0.4, I'm going to estimate that my standard deviation is about 0.4. Again, on this side, the distance between those is around 0.4. Again, those are estimations, but because that's a feature of the standard normal curve, we can make those estimations. Okay, so when we talk about the standard normal distribution, this is not specific for like oak trees or for this specific problems. This is the standard normal distribution looks the same always. The standard normal distribution is a normal distribution, but if the mean is 0 rather than say 3.5, then it's the standard normal distribution. If the standard deviation is 1 rather than some random number like 0.4, then it's the standard normal distribution. Horizontal scale of the graph corresponds to z-scores. Since we're talking about the distance from the mean, if you calculate z, you're calculating the horizontal part of this graph here. So as a reminder, your z-score that we already talked about is the value minus the mean divided by the standard deviation. So if you could change any value into a z-score, you could plot it on the standard normal distribution. So the center of my curve is the mean. We're going to change it to 0 because if you have a value right here, its distance from the mean is 0. It is the mean. And if we go one standard deviation to the left or to the right, we would say it has a z-score of -1 if it's to the left, or +1 if it's to the right. Representing that on the graph would give me my standard normal distribution. If you go 2 away, you'd be a plus or -2, so on and so forth. So I can use this if I'm trying to find the cumulative area. So if I'm corresponding to a z-score of 1.15, so that's around right here. Cumulative, we've talked before, just means that value and everything below it. So I'm going over half my curve here because 0 is at halfway point. We know 50% of it's to the left, 50% of my area is to the right. I'm going more than half. There is a chart in the back of your book, and if you don't have a calculator, that's what you're going to have to rely on, but I'm fairly certain we all at least have access to a graphing calculator, so that's the only way I'm going to explain these to you. There is a feature called normal CDF. It is in the same spot that we were finding the binomial CDF and the geometric. If you hit second bars, second distributions, it's my second feature on there. Make sure you are choosing normal CDF. We will never use normal PDF. We are trying to find cumulative areas for this. We're finding areas under the curve rather than a single value. So when we do this, we will pick the lower limit, meaning what's the smallest number we're going to include, and the upper limit, the highest value we're going to include. Then it's going to ask for the mean and ask for the standard deviation. So for this problem, my lower limit, I want it to go forever to the left. And we talked earlier when I defined this and said it never actually touches the x-axis. My x values get to -50, -5,000, -2 billion. There's, technically speaking, no end to the x values. Now, some of those are so impractical and unlikely that we don't need to include them, but we want to calculate basically the biggest, well, the smallest number we can come up with. So the way we represent that is like this. -1e99. This is your calculator's ability to use scientific notation. This is saying -1 times 10 to the 99th power. This is -1 with 99 zeros after it. It's a ridiculously small number. Yes, you can come up with a number that's smaller, but this is so small that it's going to count as practically negative infinity. It's not negative infinity. It's standing in the place of negative infinity. Your calculator has a function that is this. If you look at yours, it should be above the 7, you see a comma, and right above the comma, you should see the EE. You have to push second comma to get that EE. So if you do -1, second comma, and then 99, that'll get you your -1e99. So that's basically saying go to negative infinity, and the upper limit, we want it to stop right here at 1.15. Then we know this is the standard normal curve, so the mean is 0, and since it's the standard normal curve, my standard deviation is 1. If you put all that in your calculator, you get approximately 0.8749, and we're going to keep rounding to the nearest 10,000th in this unit. So if I'm doing the exact same thing, but for -0.24, well, that's to the left of 0, and if it's cumulative area, again, that's area to the left of it. This should be less than half. We need to make sure we're checking our answers to see if they make sense. Less than half my curve should definitely be something less than 50%. So same thing, put your second vars, your second distributions, go to normal CDF. We still want to use the same lower limit standing in place for negative infinity. We'll use -1e99 all the way up to -0.24. Still a mean of 0, still a standard deviation of 1 because it's still a standard normal curve. So it's something less than 50%. It's around 41%. Now, if I want to go to the right of 2.43, now first of all, if I go 2 standard deviations to the right, so if I take my mean and add 2 standard deviations, I'm around here. This is 2.43, so it's even further to the right of that. And I want the area to the right of that number. So if you're visualizing this, this is a really tiny little area. You should not get a large number at all. And make sure you're checking that. If you put it in correctly, you will see that represented. For this one, when I go to put this in, there's a couple ways you could do this. You could do the way we just did it, do your cumulative area and the complement of it. You could say, well, what's the area to the left? What's the area all the way to -1e99? All the way up to 2.43. Then do the complement of that, because either you're to the left of the number I want, or you're to the right of it. So that could work for you. Or I don't have that in here. That's weird. Or you could actually just, okay, so your other option that I don't know why I didn't type that up here, you could use 2.43 as your lower limit and use positive infinity. So standing in for positive infinity, you could use positive 1e99. That should get you the exact same area. So now if I say the area between a z-score of 0 and a z-score of 0.51, so if we picture a z-score of 0.51, that is not very much area at all, but I want to go between these two values. You've got two options. You could just keep doing cumulative area, the area below 0.51, but then take away the area below 0. Or you could simplify your life a little bit, not type that twice. You should know the area to the left of 0. That's dead center, so half of it is to the left of 0. So you could just say, okay, find the area below 0.51, take away 50%. Or just use those two z-scores as your lower limit and your upper limit. All three of those methods will get you the exact same area of about 20% of your curve. So now, when you get scenarios like this, we're going to get a scenario that can match this. So the SAT is normally distributed. In a recent year, the mean was 1518, the standard deviation was 308. So if I sketch this, that's the standard normal distribution. So if you sketch this, you will want your mean to be in the center, 1518. You will want to sketch in one standard deviation below the mean, so I subtracted 308, one standard deviation above the mean, 1826. Your standard normal distribution will look the same for every single problem ever. It will just have 0 in the center, 1 away, -1 to the left. Usually I will ask you to do more than one standard deviation, but apparently I didn't type that in, sorry. So for this problem, we're now going to take some student scores. We're going to change them into z-scores. We want to put it on the standard normal curve. So I'm going to take the 1406, I'm going to subtract the mean, I'm going to divide by 308. So that value has a z-score of -0.36. It's below the mean by 0.36 standard deviations. If I do the same thing for 1848 and for the 2177 and the 1186, you can see all their z-scores. Now we had talked in chapter 2 how we would know for sure that this is an unusual z-score. We said anything more than 2 standard deviations away will be considered not typical. But I want to actually use these probabilities, use these areas to prove it. So using these z-scores, I want to know which would be unusual, and not just saying, well, hey, it's 2 away, it's unusual. Let's use probabilities for this, use these areas. So find the area below each z-score. So if I find the area below -0.36, it's around 36%, not that unusual. If I find the area below 1.07, 86%, not that unusual. If I find the area below 2.14, it's around 98%. And we had said in the probability chapter that anything smaller than 5% or anything larger than 95% will be considered unusual. So this probability is supporting what we already had talked about with our z-scores. So if I found the area below -1.08, 14%, not unusual. So then if I just said what's the probability, that's the same thing as asking for an area. If I want the probability of a z-score being less than that number, you still pick your lower limit to be -1e99, -0.36, all that good stuff, you get about 36%. So because we're using probability and area under the curve as interchangeable, we can actually just change these to be written as probabilities. So if I write it like this is saying the probability of a z-score being more than 0.01. Well, I would say then that my lower limit is 0.01, and I want to go more than it. I want to go all the way up to 1e99. And since it's a z-score, I know it's on my standard normal curve. I'm still going to be using 0 and 1. So we can get our area. We can get our probability. When I write it like this notation is saying that my z-score is less than 1.3. It's also greater than -1.3. So that's saying it's going to be sandwiched in between these two. We're going to use those as our lower and our upper limits, which means I get around an area of 81%. However, for this one, we could say I want the probability of a z-score that's below -2.3, so kind of like the left tail, or it's above +2.3, the right tail. You can do these two different ways. You can see this word or and think, oh, I'm going to find this probability, I'm going to find this probability, and I'm going to add it up, and you would be absolutely correct. Or you could just realize that this is a symmetric curve. If you just find the area below the left one, the smaller one, if you double that, since it's a symmetric curve, since these scores are the same, these are the exact same areas. The area below this number is the same thing as the area above this number. Double one of them and you'll get the same thing as if you added them together. Either one works though. So this is the assignment to practice over. Good luck.